Hello, Ken.
Hey.
Good morning.
Yeah, good morning. How are you doing? That's good.
So how are you guys doing health-wise?
We're doing better. That's for sure. I'm on some new medication that's helping out a little bit. So it makes me really tired, unfortunately, but
Yeah. Your girlfriend had reactions. Have they subsided?
yeah, they've gotten a lot better. It's not completely gone, but it is 10 times better than what it was. So
Yeah, I know certain people react a lot more to this than others. Like I know at least in my family, I had very mild reactions, but my mother was down for 2 days actually, and she did not have taste for about a week or so, like at least 5 days or so.
oh well.
So it affects different people differently. It's not very clear what exactly is this. But hopefully,
Yeah,
okay.
hopefully everything will be okay. I think it will. I mean, it's not like anything life-threatening or anything dangerous. It's just,
Especially the exam week, like when there is exam next week, that's not the right time.
I know. Yeah, I agree.
Anyway, so let's keep pushing on with what we have in this course. This is the last lecture, and on Monday you have the exam, right? So you'll be done. And the exam we'll have it in person. Would expect whatever we did already. Like I don't expect to ask anything significantly different. It'll be good
Okay.
with that repetition of whatever I'm doing. Just go through everything that we've done. So technically all the homeworks are already due. So at the most, let's finish it off by Friday evening. Does that sound reasonable?
Yeah, yeah. I only have to finish homework 13, so I was gonna try to turn it in tonight. So that sounds good.
Okay, so we were doing relativity, and let me summarize. Is this still readable, what I'm writing? Is the pen got a little lighter? Should I be changing the pen, or is it?
Oh no, no, it's fine. It's fine.
So we're doing relativistic kinematics. Uh, Today will be the first time we will barely touch on dynamics in the sense that we will talk about acceleration, but we'll still not be able to introduce force. I think it will be going too far. But in principle, like we have F equal to ma in Newtonian physics, we can write the same equation in relativity. Basically, the only thing that changes is the interpretation of momentum. So remember, we have, so the quantities that we do is we have ds square is equal to minus c square dt square. So that's minus d square plus dx started with dx. That's your statement of that's a statement of invariant distance if you want. This is like saying you have a quantity which has time and position, but this whole quantity does not change under Lorentz transformation. So, right, that's the idea of something not changing, something being invariant. Based on that, we found it convenient to define our quantities like four vectors, right? So we have for position, which was x alpha, which we said was c times t, and position vector x. So the same old position, same old time, but now we are saying that they are components of a four vector in the sense that if you go in different transformations, that means to say different frames, if someone was moving, they will measure different times, they will measure different positions, but the invariant distance associated with this remains the same. That's the basic idea. So it is not should once you get used to this, it shouldn't be a surprise that oh we measure different times, we measure different positions, length contraction, time dilation. All that is a consequence of this idea. For velocity is defined as u alpha, which is c times dx alpha over ds. That's a definition, but when we actually evaluate it, we show that this is nothing but c times gamma and velocity v times gamma. That's gamma. I keep trying to write my gamma in a decent manner. Hopefully the context it is clear. And we also, and yeah, for next should be acceleration, but let's, while we are doing velocity, let's do momentum also. So momentum, right? Momentum. Key alpha is simply m, which is an invariant quantity. It is a constant, does not change between observables, times u alpha. That's it. Right? That's your momentum. And you say that since this is u alpha is already mc gamma, yeah, mv gamma. That's your momentum, and your physics comes from the fact that you say this is equal to energy, and for dimensional reasons you say that it's a c also in there, and this is your momentum. That's it. So everything, whatever we know in Newtonian equation remains the same, just that Newton says that rate of change of momentum with respect to time is equal to mass times acceleration. Now the momentum will be this new momentum, P, which is mv times gamma, and the acceleration will be our new acceleration that we will work with today. We already introduced it barely last time. So all those quantities go through, except that you want to make some very slight changes associated with momentum and energy. Here today we will talk about uniform acceleration, so we won't really talk about the force, and we will first introduce the acceleration in the relativistic sense, and then talk about what does it mean to say that something is moving with uniform acceleration in the relativistic sense. So let me now define what is force acceleration. So force acceleration will be A alpha, which is C times change the rate of change of the velocity, force velocity with respect to the invariant distance. And we can show that this is equal to C times dt, ds, and d by dt of u alpha. Just a chain rule. This we know is gamma from last time we did this, or you can go back to the first equation here and derive that this is actually just gamma. So if we can take the time derivative, the usual time derivative of your force velocity, then we have our formal expression for the acceleration. So let's do that. So that's gamma outside, and time derivative of c times gamma, which is c times time derivative. Oh, I'm in the board space. That's gamma. And here, when we take the time derivative, there are two terms, velocity and the Lorentz factor gamma. So when I do the rate of change of velocity, that will be my acceleration. Right? That's my usual acceleration, derivative of velocity with time. And that will still stay our usual acceleration. But now I can have a change in gamma with respect to time because it has velocities in it. That's your acceleration. Let's process this. You have to actually evaluate this derivative of gamma, right? So there's a lot of terms in here. What we are used to as acceleration is showing up just as one term in this reasonably rich expression or reasonably complicated expression. One feature is immediate, just to give you a feel for what this is. If you notice, if you were to set velocity, let's say this is equal to, let's say velocity is set to 0. Remember that velocity going to 0 does not mean acceleration is going to 0, right? Acceleration involves two velocities. So if the particle is at rest continuously, then surely acceleration is 0. But it is possible that it is at rest instantaneously. For example, when you throw a ball up in the air, at the very top of the trajectory, it is at rest. So velocity is 0, but it's still accelerating. Right? Acceleration is acceleration due to gravity, g. So that stays, right? So velocity equal to 0 does not mean that acceleration is 0. And that's an important concept here because we will often talk about rest frame. Rest frame doesn't mean that you're really permanently at rest. It could be instantaneously at rest. For example, if I'm accelerating, in my own frame, I'm always at rest, but that frame is keeping on changing because I'm accelerating. So those are important concepts that people struggle with in relativity. And that's important also. And I'm just saying it in passing here, but keep that in mind. If velocity is 0, gamma is 1, and if gamma is 1, this becomes derivative of time goes to 0, so that's equal to 0 here, and you have so this becomes acceleration, the usual. So when I write acceleration with a vector, so this is your Newtonian acceleration. Right? Gamma is 1, velocity is 0, that's your old. So when I go to the rest frame, I do have the fact that acceleration is a space component of a 4 vector. That's your usual acceleration that we talk about. So we are okay as far as we are in the rest frame, but the moment you start moving around, there are all these complications that come up, and we want to keep that, we want to capture that. But again, this rest frame will play an important role very soon. So let's actually get the explicit form of this. Having mentioned that, actually I don't need this at this point. I'll bring that concept back. We want to evaluate this expression explicitly. For that, I need the derivative of gamma with time, and I can use a trick for this purpose. And I use the fact that u alpha is equal to minus c squared, right? We showed this last time. We said that this tells us that the distance, the length of the 4 velocity vector is actually constant, which is minus c squared, right? The length of any Lorentz vector will be a constant when you see from different frames. It's a Lorentz independent quantity. If I take the derivative of that with respect to the invariant distance or time, then this is equal to 0. And this implies that u of alpha times a of alpha is equal to 0. Right? Again, we showed that last time. If that is the case, then there is a constraint here, right? So I have u of alpha, I can multiply that with a of alpha. It is saying that the 4 velocity and 4 acceleration is always perpendicular to each other in the Minkowski space. So let's see what is this condition. So let's multiply the time component of velocity with the time component of acceleration with the negative sign, and the space component of velocity with space component of acceleration, and that should be set to 0, right? So the equation we learn is 0 is equal to, multiply this u and the acceleration, so gamma times c, there is a gamma outside also, so this is c squared, gamma squared, and that is d gamma over dt. That's the first term, and that comes with a negative sign. Negative sign because Lorentz scalar product has a, when it multiplies two negative components, that gives you negative sign. Next, we want to multiply this with this whole expression here, and we shouldn't forget the gamma that is outside. So there's a gamma here, there is a gamma there, 3 gammas, and then there is a velocity. So there's 3 gammas, and velocity dotted with, this is acceleration. So that's velocity dotted with acceleration. Again, do the same thing here. This is velocity dotted with velocity, and there are 2 gammas. So this is plus velocity dotted with velocity times 2 gammas, and derivative of gamma with dt. That's your equation that we have. Let me divide out by c squared. Then I get a beta squared here, velocity squared over c squared. And these two are the same terms. I can take it to the right hand side, and what I get is 1 minus beta squared times gamma squared, d gamma over dt. Oops, I'm not in the word space, I guess. Right. Take this to the left hand side, and I've divided out by c everywhere, c squared everywhere. That becomes 1 minus beta square because velocity square over c square is beta square, and gamma square d gamma dt is the same thing in the first and third terms. And that's equal to then gamma cube, or let's say v dotted with a over c square times gamma cube. However, there's a simplification on the left hand side. 1 minus beta square is exactly 1 over gamma square. So this is actually 1. Right? This whole coefficient in front is actually equal to 1, because gamma square by definition is 1 minus beta square. So we have a relation here for the derivative of the Lorentz factor, which appears in the acceleration. That was the whole idea that we wanted to evaluate, like as an explicit expression in terms of velocity and acceleration. So derivative of the Lorentz factor, because the Lorentz factor has velocity in it, it involves acceleration because eventually you will hit the derivative on the acceleration, and its expression can be written in this form. Once you have this, we can go back and substitute it in the for acceleration, and we will get an explicit form for the for acceleration. So let's write that down. So what's for acceleration now? Okay, so for acceleration, A alpha is equal to, we have the expression for derivative of gamma, which is, there is a C, and then there is gamma 4, you write it as V dotted with A over C square times gamma 4. Right? 3 gammas coming from the derivative of time, and there is a gamma outside that for acceleration. That's gamma raised to 4. Right? It's like saying when we talk about Lorentz contraction, there is a factor, each factor of gamma contributes to either a dilation or a contraction. Acceleration involves, at least the time component of that involves 4 contractions. That's because derivative of acceleration involves length and 2 times in the denominator, and so on. Right? So those are the features that one has to think about. Okay, then comes the space component, which has acceleration itself. This is the dv by dt, the Newtonian acceleration, times the gamma square plus v times v dotted with a over c square, v times v dot, and then again gamma raised to 4. That's your total acceleration. That's an explicit form for your acceleration in terms of velocities and the Newtonian acceleration. So A here is Newtonian acceleration, B is the Newtonian velocity, 4 alpha is the Lorentz 4 vector. So that means that if you calculate the length of this object, length is got by squaring this, right? Take a square of this vector and then take a square root. This length of this acceleration will remain the same when measured by any moving observer relative to each other. Otherwise, if you had to try to measure acceleration, no, it won't match with someone else measuring acceleration. So, so that's a idea. Since we are talking about the Lorentz invariant quantity A alpha, so we should know what that is, right? So let's calculate that. So let's calculate A alpha. It will be messy, but it won't be that bad, right? So let's calculate that. This is equal to square of this quantity. We'll have square of this with a negative sign. That's minus c square times v dotted with a over c square, and then square 20, and then gamma raised to 8, right? 8 factors of the Lorentz factor. Then we want to square this plus, this is A dotted with A. Let me write that as vector A, magnitude square. Notice this will be a 4 vector square and this will be a 3 vector square. This is the Newtonian acceleration squared quantity, and this is the Lorentz acceleration in the squared sense. So I will always try to write the vector in that magnitudes to differentiate that. Otherwise, if I just write A, it can be confusing as to whether it is a 3 acceleration magnitude or the 4 acceleration magnitude. And that is gamma raised to 4. I can square this also, so that's the 3 terms from the square, right? So that's velocity squared here. So that's, let me write that as c squared times beta squared. So c squared times beta squared, and then square this, v dotted with a over c squared squared, and square this quantity also, that's gamma raised to 8 again. There was a gamma raised to 8 here also. And there is a cross term coming from the square, which is equal to 2 times v dotted with a. So first time let me write c square and v dotted with a over c square, and square it, v dotted with a, and then this is v dotted with a again. And there is a gamma raised to 6. This quantity, whatever that is going to be the same when measured by different observers moving with different uniform velocities, right? Relative to each other. If they were to compare their numbers of measurement, they will come out to be the same. This can be simplified. So let's simplify this. Notice these 3 factors of v dotted with a are the same, right? So first let me see that these 2 are actually can be combined. So let me show that this is equal to gamma raised to 8 is common, v dotted with a is common, and then the minus, right? So this is by the way, this was c squared, right? So this is c squared. So that's minus c squared v dotted with a over c squared square, and actually let me write that acceleration square term first because that's a different entity altogether, so that doesn't get simplified further down. That's gamma raised, so that will stay the same. It's minus c square v dotted with a over c square, and there is a gamma raised to 8, and that's 1 coming from this term, and if I write this, that's minus beta square. That's these 2 first and third term combining together, plus 2 times c squared v dotted with a over c squared gamma raised to 6. But we already have used the fact that 1 minus beta square is gamma square. So this whole thing actually is gamma raised to 6, right? Because gamma square cancels the 1 minus beta square. So it's gamma raised to 6. And after I get this as gamma raised to 6, that actually cancels one of the terms in gamma raised to 6. There's a factor of 2 here, there's a factor of minus 1 here. There's a simplification in that. And this whole thing is equal to squared gamma raised to 4 and plus c squared v dotted with a over c squared times gamma raised to 6. It cannot be simplified further, and in this form it is okay, but there are different ways you can write this. This is written in terms of the scalar product of velocity and a. It is also possible to write this as a cross product, and that's also very useful. Sometimes when you're when a charge is in an electric field, you want to write it as a cross product when it is in a magnetic field, you want to write it as a scalar product, because in a magnetic field, remember, velocity and acceleration are perpendicular to each other. And in an electric field, typically, if it is starting from rest, it is in the same direction. So there are different ways you can do it, but I won't explore that at this stage. What we want to do is, what's the interpretation of this, right? Or what can we do? So what is happening here is, that is for acceleration, and the length of that quantity. So let me say this is a alpha magnitude square is equal to the Newtonian acceleration magnitude square times gamma 4, and that is the velocity dotted with the acceleration piece in here. As you go faster and faster, so notice for each velocity, you can associate a Lorentz frame. Like if you are in a particular frame with moving with a certain velocity v, then you have this particle that is moving with some acceleration at different times. It has different velocity, and one particular velocity connects with all this, and then you would say that, okay, that's the frame in which you're in, and in any frame you can calculate this. But there is a very special frame which we will call the instantaneous rest frame. Instantaneous rest frame. Right. So there is a particle moving whose velocity is this, and now out of many frames that was possible, there is one particular frame whose velocity is exactly equal to the velocity of the particle, and that will be called the instantaneous rest frame. Often, this is just like, since you start using this so often, it is often written as IRF. Again, what does it mean? I have a whole set of frame moving with different velocity. Those are the possible observables, right? That's an infinite set of velocities possible. Out of that, there is one velocity which is exactly equal to the velocity of the particle. Like this is the velocity of the particle, and it is accelerating. In that particular frame, in that choice of that instantaneous rest frame, I can again measure my acceleration, but this is going to remain the same. Right? A alpha is an invariant quantity, that's going to remain the same, but the right hand side will be different, because gamma now will be 1, velocity is 0, it will just be A itself. But this is now in a special frame, so I will call that 0. So this is in an arbitrary frame. This is in a special frame, which is the instantaneous rest frame. That's equal to A0 on the right hand side. Left hand side will be the same, because it's the same, which means to say that this is equal to this. Like the right hand side is the same. Is that clear, the argument, what I'm trying to say?
I think so. I think it's pretty clear.
Okay. So A here will be called the proper acceleration. Let me call it the magnitude of it. Will be called the proper acceleration. Or let me say A vector A, which is the same as magnitude of A alpha, is the proper acceleration. That is to say that there exists a frame in which that can be measured this, but then once I measure that, that's what it is. So the length of the 4 vector is called the proper acceleration, and it has the interpretation that in one particular instantaneous rest frame, that's exactly the acceleration that you would measure. That's the only acceleration you would measure. Okay? And this is the same for every observer. So that is a very unique feature about it. It's like saying speed of light, right? Speed of light is the same for everyone. It doesn't matter who observes it. Speed of light is the same. Speed of light, in fact, is the length of the 4 vector associated with the particle. Right? Even if it is moving with speed slower than light, its length of the 4 vector is the speed of light. right? It's a negative of that quantity, so that says that it's finite. Similarly, if a particle is moving, it has an acceleration, and its proper acceleration is this. It's the Newtonian acceleration that would have been measured in the instantaneous rest frame. Okay, now what we are going to do is, so we are going to define what is called a hyperbolic motion. So let's do one thing, learn actually one small step. Let's stick to one-dimensional motion. One-dimensional motion means that velocity, so we're going to talk about this is a special scenario, velocity is parallel to the acceleration. Right? That means it is one-dimensional, right? Everything is happening along a straight line. So one-dimensional. Straight line. Motion is happening in a straight line. All the motion is happening in a straight line. Okay. In that case, you don't even have to talk about the vector because everything is in the same direction. Velocities and acceleration is in the same direction. We can remove the vector also, which we will do. But let's see what is the for acceleration in that case. So for acceleration, the magnitude of that is equal to the magnitude of the acceleration, Newtonian acceleration itself, and there's a gamma raised to 4. And the second term, v dotted with a, is actually b times a itself. So I'll cancel out the c squared, and I have plus c times beta times the magnitude of a times gamma raised to 6. Is that correct? Oh, there was a square here, right? Sorry. So there was a square here, right? I missed that. Right? There's a square here. Did you see that? So I added a square here. I missed copying that square.
Yeah, actually, I had the square there.
You wrote it down probably.
Yeah, I think you said it, but you just didn't write it.
So this is acceleration square, and this is beta square. And then there will be an extra c square, right? So that's helpful. So then that's just beta square, I guess. Is that right? Acceleration, yeah, that's correct. Dimensionally, acceleration, and beta, and then there's a gamma raised to 6. So in one dimension, there's a simplification of that kind, right? That dot product is not necessary. And there is a significant simplification now, because this can come out. So this is a. Oh, this is square again, sorry. Left hand side is square, yeah, I think now it's okay. So that's gamma raised to 4, and that is 1 plus beta square times gamma square, which is 1, I want to write it as 1 minus beta square. That's just algebra. But now notice 1 minus beta square plus beta square, if I make the denominators the same, the numerator becomes 1, denominator is 1 minus beta square, that kills a, that's basically gamma square, right? So that's gamma raised to 6. Again, I raised to 2. So this is equal to magnitude of a square times gamma raised to 6. What it means is that a alpha magnitude is equal to the acceleration times gamma cube. And this is also A0, right? So that's a rest frame. Right? This is a statement, if you want like length contraction, how do you write it? You would say that length measured in the rest frame right, is equal to length measured in the moving frame, right, and divided by gamma. No, length measured in moving frame is length measured in the rest frame times gamma. So this is the statement of length contraction, right? So in a rest frame, it is always larger by what is measured in the moving frame. So this is a factor of gamma that comes in. Very similar here, proper acceleration also contracts, but now it doesn't even not only contract, it contracts by a factor of 3 times the Lorentz factor. So it contracts significantly. Right? That's the way to see it. But we are interested in actually, so when we say that, so from this point on, when I'm going to say that a particle is moving with uniform proper acceleration, that means I'm fixing this, right? And this is a Lorentz invariant quantity, so I can do that. But that doesn't mean that the Newtonian acceleration is fixed. Newtonian acceleration times gamma cube is what is fixed. Okay, is that very clear?
Yes, that's clear.
Like we have length contraction, acceleration contracts, and it contracts by a factor of 3. And we will say that this is constant, and we'll talk about the motion associated with it. So this is one-dimensional motion, and this is often called hyperbolic motion. And the reason why it is hyperbolic will be clear because the solution will be a hyperbolic. So this is hyperbolic equation. Often it's called hyperbolic motion, not equation. Motion. Rindler acceleration, or just proper acceleration. It's a one-dimensional motion, and remember when I say the answer is going to be hyperbolic, this should be contrasted just for having an insight. If there was a particle moving with uniform acceleration in Newtonian physics, then you would get a parabola, right? A uniform acceleration is governed by a parabolic motion, but now it's going to be hyperbolic motion. So let's see what it is. So we are saying acceleration is constant, which we will say is a naught. Right? A naught is fixed. So this is your proper acceleration, but proper acceleration is just a. So now I'm not going to write it as a magnitude of a. So this is gamma cube. So here, whatever a naught is proper acceleration. And a is your dv by dt, right? which is your what do you call the usual Newtonian acceleration. And gamma is the 1 minus beta squared. That's our expression for acceleration. Okay. One thing immediate that comes out. So we would like to solve for position, right? So this is a constant, right? This is constant. So our statement is that dv by dt, let me write that as d beta by dt. So there is a c then there, right? So there is a c times gamma cube is equal to c times or a naught. That's a constant. That's the equation we want to solve. Remember, if you're doing Newtonian physics, you would say dv by dt is equal to a constant, which is acceleration, and immediately integrate, right? Integrate this and say, oh, at plus a constant. Integrate it again, and you will get x is equal to half at squared plus, let's call it v naught, plus v naught times t plus a constant, right? X naught. That's what you would have done in Newtonian physics. We want to do the same thing here, integrate this 2 times, you get what's the path taken by the particle. That's exactly what we want to do, and we want to use some tricks. Right? So to get the integral, we have to integrate this dt now. So there's a velocity. I want to separate it out, right? So the first observation is, right? If you want, let's make the observation that d by dt of beta times gamma is the same as d beta by dt times gamma plus beta times d gamma by dt. That's straightforward. But d gamma by dt, we know we calculated that earlier. So that's d beta by dt times gamma plus beta times, we said we did that for a general scenario, but now we are in one dimension. So that's nothing but beta dotted with a over c, if you want, over c, right? Because acceleration has this one of the velocity and this is okay. That is extra derivative here, right? I think that's correct. No, beta, let me write this as gamma cube. Okay, let me check this. D gamma by dt, right? D gamma by dt is this velocity is replaced by beta over c times gamma cube. That's correct. And I already written one of the beta. So is it dimensionally correct? So I have a 1 over time here, and the beta is dimensionless. So 1 over time. Yeah, that's correct. Okay. But I'm doing one dimension, so I don't need this vector, right? I'm in one dimension, so I can forget this vector. So that's A is velocity. So A is now dv by dt. So that's the same as d beta. So d beta by dt times c. So that makes this d beta by dt better. Okay, much better. Is that okay? Yeah. So that's equal to, let me pull out a gamma d beta by dt, and that's 1 plus beta square times gamma square. But we saw this expression right some time back, right? So this is the same as gamma times d beta by dt times 1 plus beta square over 1 minus beta square. But that's the same as gamma cube. Okay. So what we have shown is that when we say, so this is the statement of uniform acceleration, right? When we say statement of uniform acceleration is that acceleration times gamma cube should be a constant. That statement immediately tells us that this quantity is a constant. So I can say d by dt of beta gamma actually is equal to a naught over c, which is a constant. That's a proper acceleration, which we are keeping fixed. Any questions at this stage, Ken?
No questions. No questions.
So if I were to integrate this, I will get the velocity, and the idea is that I will integrate it 2 times and I'll get the path of the particle. So integration in this form is easy. I just do it on both sides. So I evaluate this to be beta times gamma. Let's go starting from one point to the other. So let's say beta times gamma. Do I want to start from rest? Minus, let's say, beta times gamma So our beta times gamma evaluated at two different times, right? So at T1, at time T and some T0, right? That's equal to A naught over C times T. Cannot be simpler than that. Let's say it starts from rest, right? So let beta at time T equal to 0 be equal to 0. So it starts from rest. So then the second term goes away, and what we have is beta times gamma is equal to A naught over C times T. We want to solve for, or let's solve for velocity at this state. So let's square this. So that's beta square over 1 minus beta square is equal to A naught over C times T the whole square. Okay. Let's solve for beta. I multiply by beta and then bring it on the other side. So just doing algebra here. So this is the same as beta square of 1 plus A naught over C times T square is equal to A naught over C T the whole square. So I divide that out and then solve for beta. So it's beta is equal to square root of that. So this is A naught over C times T divided by square root of 1 plus A naught over C times T. Beta, remember, we shouldn't forget, is the x velocity, right? Velocity over c. So let me explicitly say that this is dx. In one dimension, it is just dx by dt, right? So if I integrate this, I will get my position. Remember, if we were doing Newtonian physics, we would only get this term, right? If you're starting from rest, this will be just velocity times t, right? So you don't get this denominator term, and then when you integrate it, it becomes 2 squared. So this denominator is the new part coming due to the relativistic feature that we are talking about. So let's integrate this, right? So let's integrate this, and we should get our solution for proper relativistic acceleration, or relativistic uniform acceleration. So let's say this can be done as, so how do I want to do this? Yeah, so let me first write this as dx over c, the dx over c as it sits, times dt times a0 over c times t divided by 1 plus a0 over c times t squared. It seems like there is an a0 over c coming always with time, so let me do that. That's a constant, so I say I multiply by an a0 over c here, and then I do the same thing on this side also, right? So a0 over c on the left hand side. Okay, so and yeah, that's it. And I have to integrate this on both sides from some, let's say 0 time, sometime to later time. So let's say 0 to, instead of doing that limits, let me say I'll capture this as a constant, right? So this will be equal to a0 over c squared times x plus some constant. Let me say some constant is, how do I want to write that? Yeah, x naught, right? Let's say a naught over c squared times x naught. Right? So this is a constant of integral, and I integrate this left side of minus, right? It doesn't matter whether it's minus or plus. Some x naught, which is a constant of integration, which I've written it as a naught over c squared. Let me substitute this a naught over c times t. Yeah, t is equal to, what should I substitute here? Did I miss something? Is it a minus or plus? Let me just check. Oh, I make mistakes by any chance. Yes, okay. So let's actually substitute this whole thing as 1 plus this whole denominator as something. What should we substitute? What's the letter you can think of? STUW, right? So that's a W. And then if I take the derivative, so it will be 2 times A0 over C times T times A0 over C times dt will be equal to dW. So this is just 2 times. So the numerator apparently is integral of dW over square root of W, which is the, no, that is a factor of 2 also. Factor of 2 also, 2. Which is the same as W raised to minus half plus half over 1 by Q. Right? So that's the same as square root of W. Right? W is that. So we have our solution a naught over c squared times x minus a naught over c times c squared times x naught to be equal to 1 plus square root of this right? Yeah. Okay, so let's simplify this a little. It's just a matter of rearranging. So let me write this as a naught over c squared times x. Yeah, so at this point, this is a, let's, before I proceed and simplify this, let's say, again, this is a constant of integration, right? X naught. So let me see what happens at t equal to 0. At t equal to 0, I have to specify where my particle is. In principle, it is usually convenient to put it at the origin, right? But we don't want to do that. This is just for, this is again a trick, just for simplicity. Let us say that at t equal to 0, x as a function of time is equal to, let's say, I need a distance. So this is c squared over a naught. Okay. Yeah, I think that's what I want to say. Let me check my notes here. x at c square over alpha. I think that's what alpha is, you know. Okay, good. I think that's what it is, if I remember this right. So what we have is, substitute this here, then I can solve for x naught, right? So this is a naught over c square at x equal to 0. This is c square over a naught minus a naught over c square. X naught is equal to 1, and this is 0. Correct. I think so. Why am I struggling? Hold on. Give me a second. I think I'm missing something here. Yeah, that's okay. Actually, this is okay. Yeah, this implies, yeah, this is okay. This is what I wanted. Yeah, so this is 1 minus a naught over c square times x naught is equal to 1. The 1 cancels out. This implies that x naught is equal to 0. Yeah, so I was wanting a choice in this initial condition which will set my x naught equal to 0. That's being tricky there. But that just, when I'm very soon going to graph this, and that is just a convenience for that purpose. Did I confuse?
Can I ask why it's equal to 1?
Oh, because at time t equal to 0, the right hand side is 0.
Oh, I see.
I'm substituting this in this equation. T is 0, x is this. I get this, right? This is how you set your initial conditions.
Right. Sorry. Thank you.
So x naught is equal to 0, and then I get my solution in a slightly easier form. Like plotting becomes easier with this, that's all. And I'll tell you in a minute why that is the case. Okay. So this equation seems like, oh, how do you plot this? Let's rearrange this so that we see the actual form. Y is hyperbola. This is an hyperbolic equation. Square this and bring this on the other side. So this is a naught over c squared times x squared minus of a naught over c times t, the whole square is equal to 1. Notice this equation, when you have an x squared plus y squared is equal to 1, that's a circle. If you have x squared plus y squared with different scales, that's an ellipse. And whenever you have a minus, that's a hyperbola. So this is an hyperbolic, this is a equation of a hyperbola. And in what sense, where does it sit in this frame? Let's do that. Well, if I were to square this and put this all on the right side, I have x squared minus c squared t squared, so ct the whole square. That's equal to a naught over c squared, or c squared over a naught. C squared over a naught. Remember that was a constant right there. Square. So remember at x equal to 0, your position was here. When I set time t equal to 0, x is exactly this. Where is this equation sitting in? If I were to plot this, that's my position and time. And let's say this is my space-time diagram, right? So this is my x as a function of time. That's my c times t. And that's a straight line representing the speed of light. That's a light cone if you want. And that's your line. I'm starting from not from x equal to 0, but from a finite value. So that's your c square over a naught. At that point, at x at time t equal to 0, that's your x0. Right? So that's x of 0, which we chose to be c square over a naught. If I start from origin, it's just that it's shifted, and I'll show you in a minute, then the drawing the hyperbola becomes difficult. If I were to plot this, this looks like this. That's your hyperbola. The question is, what's a hyperbola passing through the origin? Yes, it is. You can always do that, but its asymptote then is not passing through. It's not the speed of light. Now you can ask, what is the good feature about this? This never goes faster than light. This particle, even though it is uniformly accelerating, with proper acceleration, this never goes faster than light. In fact, the maximum it can do is it can approach the speed of light. That's the good part. If you were to draw like the same path for x equal to half at square, right? I can say x minus x0 is equal to half at square. Right? So that's your Newtonian particle. How will it look like? It will start from here. So let's say this is again the parallel line. That's a speed of light cone there. If I were to do a parabola will look like this. And you notice that very quickly it crosses the speed of light. And it is not that crossing is important, it is a tangent that is important, right? So very soon, notice if you are having a constant here, so the moment the slope becomes larger than speed of light, you're going faster than light, and that's not allowed. So Newtonian parabola violates relativity, but your proper acceleration does not. But nevertheless, before you start going faster than light, there is a very small time period here where actually these two should be looking the same, right? When I throw the stone up in the air, I don't have to worry about relativistic acceleration. In some limit, this should approach that, right? So let's go back to this equation and see how that works. So let's go back to this equation here and actually solve that for small times. So let's say this is 1 plus a naught over c times time square. But now let's say t is very small compared to c over a naught. So that's a scale in the problem. C over a naught is a time. Let's say that that's a very small time. That means to say that in this region, time is very small. Very small time there. In that region, I can expand this and I'll get 1 plus half a naught over c t squared and so on. There are higher order terms in there. Multiply this with a naught over c on both sides, so I get x is equal to a naught over c squared plus c square over a naught. So c square over a naught plus half of c square over a naught cancels one of the accelerations. What is left out is a naught t square plus higher order terms, which is exactly the Newtonian equation. So this is x as a function of time is equal to x of 0, right? Because c square over a naught was x of 0 plus half a naught t square. Fits in very nicely with the Newtonian physics for small times. As far as you don't allow that particle to go too fast, because it very quickly will start going too fast because it's accelerating. But if you're in very small time periods, it's very Newtonian physics works. And I chose my x naught. Now it's very clear that why I chose that x naught with a very specific value that allows all this equation to be very simplistic. Otherwise, there is that added baggage that you have to calculate, carry on with it. It's just for that simplification. There is nothing magical about it. Oh, was my screen not capturing everything? Sorry.
Oh no, you're good. I got it.
Yeah, so I'll stop with that. Good place to stop. And yeah, thanks for listening.
Oh yeah, no, that was beautiful.
Okay, and again, as I suggested, just go over all the lecture notes. I will pick few things, just small pieces of derivations here and there that can be done in an hour or so for the exam, and that's what will be asked in the exam.
Okay. I just want to like confirm the exam is cumulative, right?
Let's make it mostly at the end part more, like about 80% of what we did after midterm two,
Okay.
right? So basically the
Okay.
Kepler problem, the perihelion, and relativity, right?
Okay.
What we did later on, yeah.
Yeah.
Kepler problem, perihelion shift. Probably one problem on Kepler, one problem on perihelion shift, and one problem on relativity, something like that. 3 problems which are each can be, if you know what exactly how to do it, probably it's only 15 minutes. But if you don't know what you're doing, then probably it can take maybe half an hour because you struggle a lot, right, during the exam. Assuming that you take half an hour for each of the problems, that's 1.5 hour exam kind of. So something like that. So just go over the homework and the lectures. That's all.
Okay.
Don't sweat too much. It's just a matter of finishing. Homework and all was more important. And as far as that all, that's good. Okay.
Okay. Sounds perfect. Thank you, Shujesh.
Yeah. Okay. Good luck. All the best.
Oh
I'll see
yeah.
you
Thank
on
you.
Monday, I guess. Yeah.
Yep. I'll see you on Monday. Goodbye.